Good morning, ladies and gentlemen. My name is John Moroney, Business Support Manager here at Hach for the UK and Ireland. Just wanted to welcome you to our fifth in our current series of webinars from Hach on wastewater applications. The presentation this morning will last approximately 20 minutes. And as always with our webinars, we'll keep the questions until the end of the presentation when we'll answer them, and if need be, we can take them offline to discuss them with you further. The way to ask the questions, if this is the first time you've been on one of our webinars, just type it into the panel on the left-hand side of your screen, and we'll get to those, as I said, at the end of the presentation. The fifth presentation in our series this morning is simply entitled DAF Optimisation. It's presented by Martin Butterfield. Martin has worked with Hach for the last 20 years and has been in the water industry for some 30 years now. So he has a wealth of experience to kind of bring to this subject. Martin is our application development manager and a real-time control optimization specialist. So I'll pass you over to Martin now, and I'll speak to you all at the end when, as I said, we go through any questions that you may have. Over to you, Martin.
Thank you, John. And good morning, everyone. Before I begin speaking about the DAF process, there are a number of similar sounding treatment processes that I'd like to take a few moments to clarify. First of all, the process I'll be talking about, and that's DAF. Now, DAF stands for Dissolved Air Flotation, and this treatment process is primarily for solids removal. Another similar sounding process is BAF, B-A-F-F. This stands for Biological Aerated Flooded Filter, and is a treatment process designed for BOD and nutrient removal. It consists of treatment cells, each having the biomass growing on some form of small plastic media, which is mobile. The media being retained within the cell by a mesh or perforated screen. Another similar sounding process is SAF, and that stands for Submerged Aerobic Fixed Film Reactor, sometimes just as a single F or sometimes with a double F. The SAF process is similar to that of the BAF, but in this case the media in which the biomass is growing is not mobile and does not need the screen or mesh to retain the media. Having said all that, the process being discussed in this webinar is the DAF, or Dissolved Air Flotation process. The DAF process was invented and developed in Sweden in the early 60s. Over the years, the DAF process has been refined since that time, permitting lower hydraulic residence times and higher loading rates than on the original installations. It is important to stress that the DAF process is not a biological process, unlike the others previously mentioned. It's merely an enhanced solids removal process which works best with solids that have specific gravities of around 1 or less, as these would be difficult to remove in a normal gravity-driven settlement tank. DAFs have a much smaller footprint than a conventional settling process due to the short retention times of the process. When the DAF process is used as a first stage clarifier for reservoir water treatment, there is a distinct advantage in this short residence time, as algae do not have the chance to degrade and release their cell contents into the water. This reduces chlorine demand and the risk of taste and odour issues being created in downstream processes. Another reason for using DAF processes, as algae are present throughout the water column, their SG would be very close to 1, which would make gravity thickening impossible, and so potable water treatment sites have to use other methods such as pulsators, which are not the subject of this webinar. The DAF process consists of 4 main parts. The mixer and flocculators ensure that the even dispersal of the flocculant and polymer within the sample, and are sized to ensure the floc has sufficient time to develop before it enters the clarification process. The saturator is where the recycled water is saturated with air to form fine bubbles used to float off the solids. The equipment and process for this key stage is covered later in this webinar. The DAF tank itself is where the solid separation occurs. Note, some solids are not floated and do settle into the base of the DAF tank, so sludge collection from the base of the DAF is required. Floated sludge is removed by a skimmer or scraper and transferred into a hopper for further concentration. The DAF schematic shown on this slide shows the settling sludge being thickened by a lamellar separator. Other designs may simply use conical sludge collectors or similar. Although the mixer and flocculator are often shown as separate tanks, this is probably only true for DAF used in potable water applications. For industrial applications, both of these parts of the process are in a serpentine section of inlet pipework, where flocculant and then later polymer are added. Mixing can be achieved without a motorized paddle by using a static mixer installed within the pipe. pH correction may be required to ensure both the flocculant and polymer are operating at their optimum pH. The flow rate through the pipe is relatively low, giving the floc time to form, and at these low velocities laminar flow occurs, which exerts a minimum shear on the flocs, thus preventing damage to the delicate floc formations. Due to the low residence times in the modern DAF tank, the ideal floc is described as a pin floc. As the name suggests, the floc particles are small, making them more robust than larger flocs. For small flocs, the bubble size also has to be as small as possible, as large bubbles rise faster and would floc, but more on that later. Moving on to the saturator. This is an important part of the DAF process, as this is where the formation of the microbubbles which lift the floc begins. In general, the normal flow rate through the saturator is around 10% of the inlet flow, but on a highly loaded DAF tank, this can be up to 100% of the inlet flow. The aim of the saturator, as the name suggests, is to saturate the water with air at an elevated pressure. The two types of saturator and the different ways of dissolving air into the water are described in the next two slides. An EDUCTOR can be used in a number of configurations of saturator tanks, but the principle of operation is always the same. The velocity of the input water is increased due to the constriction at the nozzle tip. As the water exits the nozzle, it produces a low pressure area around the input nozzle due to the increased velocity, drawing in air through the suction port. The outlet nozzle is designed to create turbulent flow to ensure good mixing of the air and the water, and the back pressure on the system causes the air to dissolve within the water. The EDUCTOR may be internal or external to the saturator tank. For those who have worked in laboratories, the principle of operation of the EDUCTOR is exactly the same as the water-powered vacuum pumps used when you're filtering samples. Some similar systems use air and water passing through impellers of a pump to entrain the air, and in these cases the EDUCTOR would be part of the pump. In the packed saturator, clarified recycled water from the DAF is passed down a column packed with inert material. Compressed air is introduced into the saturator at a pressure of around 4 to 6 bar. This process of passing water over the inert material increases the surface area of the water in contact with the compressed air within the vessel, saturating the water with air. Ideally, this operation should happen at as low a temperature as possible, which increases solubility gas within the water. As stated previously, the DAF process is purely a physical process for the removal of solids from the waste stream, and no biological treatment is intended within the process. So you would think the relative solubilities of nitrogen and oxygen play no part in the efficiency of the treatment process. However, As oxygen has a higher solubility in water than nitrogen, as can be seen from the graphs on the right-hand side of this slide, the head space in the saturator soon becomes enriched with nitrogen, and eventually this will reduce the efficiency of gas transfer into the liquid phase by around 9%. This should be taken into account when calculating the energy efficiency of the DAF process. The solubility of air in water is shown against applied pressure, indicating that the higher the pressure, the more air dissolves. However, the limiting factor here is the energy consumption and the manufacturing costs when dealing with high pressures. As you would expect, the solubility of gas in water is related to the pressure of the gas in contact with the water, and its solubility is described by Henry's gas equation, which is described as a constant temperature, the amount of gas dissolved in a given type and volume of liquid is directly proportional to the partial pressure of that gas in equilibrium with that liquid. Which put simply is the obvious statement: the higher the pressure of the gas in contact with the water, the more gas will dissolve in it. Here we have a schematic drawing of a DAF tank. The mixer tank disperses flocculant and polymer throughout the water to ensure the floc forms evenly throughout the incoming water stream. In the floc tank, the velocity of the liquid is much lower, applying only low shear to allow floc to form. As mentioned earlier, both the mixer and the floc tank are often installed not as separate tanks, but are formed within a serpentine tube of large diameter to give time for the floc to form. The mixing being carried out by a static mixer to create turbulent flow in the first section of the pipe. As the water flows along the pipe, turbulence subsides, allowing the delicate floc crystals to form. The recycled return water is taken from the clean water end of the tank, passed through the saturator, and then through a sparger or pressure relief valve, which causes the dissolved gas to come out of solution in the form of microbubbles. The size of the microbubbles formed depend upon the pressure of the saturator and the physical dimensions of the sparger. It is the microbubbles which attach to the floc and solids and lift them to the surface of the tank. The scraper mechanically removes the floated floc and solids to prevent resuspension. Here we see a typical DAF tank where the mixer and floc formation zones are external to the DAF tank within the serpentine black tubing. In most cases, this is the normal configuration of a DAF system. Separate flash mixers and flocculators are mainly reserved for the DAFs in potable water applications. The bubble rise rates are not shown here, as in some ways the bubble rise rate, which is measured using clean water in the tank, is not applicable. In this case, it's the rise of the floc particles with removed solids and bubble attached against bubble size, which gives a more real-world indication of the efficiency of a DAF. Please note, the oscillation on the lines with the largest bubbles and smaller floc size. This noise diminishes as the floc particle size increases, and hence the number of microbubbles attached. Although I've not been involved with this measurement, I believe that this is maybe due to turbulent flow of the bubble, similar to that in a glass of sparkling water, where the small bubbles rise to the surface unhindered, but larger bubbles show an oscillation as they make their way to the surface. The reaction of the bubbles rising through a column of water are defined by Stokes' law. There have been many papers published on bubble rise rates and applications of Stokes' law, which is related to the force on a sphere as a fluid passes the sphere. In this case, it is the velocity of a bubble as it travels up through the water column, and the relationship between the velocity and the size of the bubble and the viscosity of the liquid. For the purposes of this webinar, we shall just say that the smaller the bubble's diameter, the slower it will rise through the water column. This is due to smaller bubbles having a lower buoyancy, and their volume to surface area ratio reduces, meaning the drag in the bubble by the viscosity of the water increases with reducing size. As mentioned, the rapid pressure release on the recycled water causes the production of microbubbles. However, the recycled water may also act similarly to a fizzy drink, in that there will not be an instantaneous, complete desaturation of the water. If this were to happen, then fizzy drinks would not really exist. If we think of a glass of carbonated water again, bubbles still continue to rise from fixed points in the inner surface of the glass. These points are known as nucleation points, being either dust particles or slight roughnesses on the surface of the glass. In the case of a DAF, the nucleation points for the dissolved gas form bubbles on would be the flocks themselves, or any other particles suspended in the water. Once the flock and particles have been floated to the surface, the floating sludge layer is then removed by physical scraping or skimming off of the buoyant sludge into a hopper. The removal direction usually being in the direction of water flow through the tank. Some manufacturers prefer countercurrent removal direction, with the idea that the major solids removal occurs directly above the sparger, this being where the bubbles are introduced, and hence the most sludge would be likely to be formed. In this orientation, the idea is that the sludge is removed quicker and has less time for the bubbles to detach, causing larger sludge particles sinking to the bottom of the tank. Another method of sludge removal is by periodically raising the water level within the DAF tank, flushing the floating solids into a launder or over a weir. This method has a drawback that water will inevitably be carried over the sludge, reducing the solids content of the removed sludge, meaning any downstream thickening process would have to remove more water. Depending upon the influence water's properties, solids contents and the design of the DAF, a secondary sludge removal system usually exists at the base of the DAF tank. This normally consists of lamellar plates or could simply be settling cones. DAF tanks do need maintenance. Because packed saturator tanks use effluent from the DAF tank, this recycled water can contain nutrients, which encourages the biomass to grow on the surface of the packed material. As there is a plentiful supply of oxygen and a warm environment, over time this build-up of biomass will cover the surface of the inert material, reducing the surface area of water in contact with the compressed air, and hence reduce the absorption of gas into the recycled water, and therefore the saturation efficiency. Eductors are also not maintenance-free. The nozzle or pressure release valve where the pressure of the recycled water is released, causing the production of microbubbles, is particularly prone to erosion due to the high velocities and different densities of water and air. This erosion will inevitably wear away the surfaces of the pressure relief valve, reducing efficiency and affecting the bubble size. The solids loading rate needs to be checked to ensure the DAF is not overloaded, which would result in poor effluent quality and hence load entering the saturator with the risk of reducing efficiency of gas transfer. Also, the bottom of the DAF tank needs to be periodically desludged, the frequency of desludging being totally site dependent. Too frequent desludging results in low solids, but infrequent desludging could mean the solids content is too high to pass through valves or pipework, requiring a complete shutdown. Other factors that affect the efficiency of the DAF are the solids loading rate, which is the amount of solids being fed into the separation process. As the solids load increases, the recycle flow will also need to increase as well, as do the flocculant and polymer dose to ensure efficient removal of the solids. The hydraulic loading rate of the DAF is also defined as the volume of water to be treated divided by the surface area of the DAF, and this results when using SI units in a rather unusual dimension of meters per hour. However, if the design hydraulic loading rate is exceeded, a number of issues can occur. Firstly, the increased flow and hence reduced residence time in the floc tank will result in the floc not being fully formed. Secondly, even if the recycle rates can cope with the increased hydraulic load, the water will not spend sufficient time within the DAF tank for the bubbles to rise to the surface and remove the floc and solids. This will result in poor solids removal and hence poor DAF efficiency and effluent quality. This slide shows the typical industries using DAF technologies for solids removal. Industries like DAF processes, due to their small footprint and the ability to remove solids with specific gravities close or less than that of water, and the process is rapid compared to other solids removal processes. For potable water, DAF plants are excellent for clarifying reservoir water, but for the removal of suspended particles including algae, plankton and diatoms. The rapid solids removal rate of the DAF means the cell contents are not released to taint the water or increase chlorine demand. For modern drinking water plants, the lower footprint compared to, say, a slow sand filter means the plant capacity can be radically increased, even more so when the DAF plant is formed on top of a rapid gravity filter. An example of this is the cocoa DAF, where cocoa stands for counter current. Here the separated sludge rises and clarified water flows down through the rapid gravity filter. DAF has also been trialled in municipal wastewater treatment works, mainly in the Netherlands. One trial in Eindhoven in 2013 reported removal rates of 73% of solids, 56% COD and 60% total phosphorus. A similar trial at another site reported 90% solids removal, 55% COD removal and 85% phosphorus removal. During this latter trial, several arrangements were tried, initially with the DAF located after the primary settling tank, and then with the DAF receiving screen sewage. Other options were operating the DAF on air only, and then adding coagulant and polymer. The stated high removal rate of total phosphorus is not surprising given the combination of the solids removal rate and the addition of ferric chloride, which would chemically react with any soluble phosphorus present. But more information on this is available at the web address shown on this slide. DAF plants have also been used as a tertiary treatment process, especially on sites suffering poor sludge settlement in final settling tanks, risking both the solids and total phosphorus consent. The efficient solids removal and the addition of metal salt could be brought online when final effluent quality begins to deteriorate. Determining the efficient operation of a DAF plant is difficult without data on hydraulic loading and solids loading. However, it may be possible to get an indication of how the process is operating if the DAF tank is fitted with a sight glass. In this picture, the floated sludge cake is quite thick, and the turbidity of the effluent is good. So it's easy to say that the DAF plant is operating well in removing solids. But is it efficient? The thick sludge layer could indicate the upstream process has a problem, and product is being lost to the effluent stream. In this situation, the sludge layer is visibly much thinner than that in the previous slide, and the turbidity of the water appears to be higher. In this case, the options could be that the DAF is not operating efficiently and not removing all of the suspended solids. But the DAF could be underloaded. The recycle rate and the turbidity could be caused by microbubbles not dispersing due to excess polymer. In this picture, we see a DAF tank with no sludge cake at all present in the water surface. The turbid water could be due to solids still in suspension, which would indicate that there is insufficient flocculant being added or insufficient recycled flow to remove the floc. Alternatively, the turbidity could just be due to microbubbles released from the recycle flow. The only way to be sure is to measure the load entering the DAF. Over the last 10 years, Hach have developed real-time control to improve the efficiency of wastewater treatment processes. One of the latest RTC systems is the DAF RTC. This can be configured to operate on either suspended solids as the control parameter when the load present to the DAF is purely in the solid phase, or true TOC when the load to be removed is present in both the solids and the liquid phases. I should clarify my previous statement, as originally I did say that the DAF process is a solids removal process, but the flocculation process can also remove dissolved compounds. The flocculant is added in the liquid phase, but transitions into the solid phase. And in the liquid phase, the flocculant can react with other chemical species, forming a solid. A common example of this is the removal of orthophosphate by the addition of acidic salts of either iron or aluminium. The metal salts react with the phosphate ion, producing an insoluble metal phosphate, which then form fine floc crystals, which in turn entrap suspended particles by surface adhesion. In this way, flocculation can remove dissolved organics from the sample stream. Just going back to the TOC analyzer, Hach's Biotector TOC is, in our opinion, the best in the market for challenging conditions of high solids loading that can be found in a DAF tank, as it is able to ingest and digest soft particles of up to 2 millimeters in diameter, giving a true TOC value. If the loading is exclusively in the solid phase, then the Hach Solitax probe is more than capable of making the solids measurement and requires minimal maintenance. Now turning to the RTC itself, all RTC systems for wastewater look at the load to be removed, and hence we measure both the flow rate and the concentration of the parameter to be removed. In the schematic shown, the TOC load is measured at the inlet of the DAF process, and the feed-forward part of the RTC calculates both a flocculant dose and consequently a recycle rate to ensure that there are sufficient bubbles to produce to lift the floc to the top of the tank. In common with most of our RTC systems, there is also a feedback or closed-loop element, where the resulting water quality is also measured and compared to predefined set point. Should the result of the measurement deviate from the target value, the feedback controller trims the floc and recycle rates to achieve the value required. By using this form of real-time control, the DAF tank is always operated at its optimum, saving energy and chemical costs when the load is low and ensuring compliance when the load is high. This slide shows the parameters controlling the efficiency of the removal of load from a DAF tank when the visualization of an RTC system controlling the solids removal process. The specific dose rate is defined as the amount of flocculant or polymer required per unit weight of solids to be removed and is determined by jar test. This does rely on consistent polymer and flocculant quality and a stable inlet load. Without determining the load to be removed, standard DAF control systems would increase the flocculant addition when the inlet flow is high, making the assumption that a high flow equals high load. But it could just be clean water entering the plant, meaning unnecessary chemical and energy costs have been incurred. It is our experience that the operators of wastewater treatment plants are busy people, and they're only able to make 1 or 2 tests per shift to adjust the chemical addition to a plant for optimization. Between those samples, the influence strength goes unmonitored and could fluctuate wildly. This is the reason for applying real-time control to any process. You can only control a process if you can measure its key parameters, and to control it efficiently, those key measurements need to be made frequently to cope with variations of incoming load. The DAF RTC makes continuous adjustments to the flocculant and recycle rates, ensuring the optimum performance of the DAF plant. This is the case even when there are issues with the quality of the dosed flocculant or polymer, as the feedback controller will detect any inefficiency and increase the dose to compensate to keep the process compliant. The bubble size formed by the recycle returned from the saturator is based on the pressure of the saturator and the physical properties of injectors. The RTC does not alter the saturator pressure, but any inefficiency in the saturator will again be compensated for by the RTC's feedback controller. The scraper speed is again related to the incoming load, and hence the load removed, the higher the load removed, the higher the load entering the DAF. Then there is a higher amount of solids formed, when there will be need to be removed before they build up. As with any process, to be able to understand what is happening, the operator and any control system need to have relevant and reliable information on the load being presented to the treatment process. For example, in a dairy application, a TOC measurement would be required as the load is both in the solid and liquid phase. And as mentioned earlier in this webinar, the flocculation process is able to remove both particulate and dissolved load by the action of the growing the floc crystals. For industrial applications, the incoming load is an indicator of how well the production process is being operated and managed. The higher the load entering the wastewater treatment process, the more saleable product is being lost, not only losing income, but also increasing the treatment costs, and so the bottom line gets hit twice. Moving on to the outlet load exiting the DAF, when compared to the inlet, using the real-time data, a simple calculation can be made on the real-time efficiency of the DAF process, which can show up both short-term issues such as poorly matured batch of polymer, or long-term issues of perhaps problems with the recycled water saturator. If these efficiency figures are compared over a longer time frame, then it's possible to show long-term effects such as erosion of an eductor or sparger. None of this information would be available from a spot check on solids or a COD test. Now moving on to compliance. Continuous monitoring of the outlet of a DAF not only shows the efficiency of the removal process, but indicates what load is being fed forward to a downstream process, be that on-site biological or a discharge to sewer. In either case, the more load being passed forward, the higher will be the downstream costs. When real-time control is applied to the DAF process, the software adjusts the process parameters to suit the incoming load, and by incorporating a feedback element, any variations in the process efficiency caused by variable chemical quality can be compensated for. RTC also provides the operator with information on the incoming load, indicating when peaks are occurring and when upstream processes which may indicate issues. Stability of the outlet load also gives a stable cost for further treatment or charging. Operating a DAF at its optimum efficiency will inevitably reduce running costs and produce less sludge, as only the appropriate amount of flocculant is added, and not, as is often found, that the flocculant is added to cope with the maximum load expected, and for the majority of the time, this is a massive overdose. In this slide, and the one following, I'll just go through some issues that we see. This picture shows an installation by an unknown contractor. The plant operator complained that the solids probe had never worked, and it's quite easy to see why. Although the solid tax probe has been installed facing the flow, which is recommended, there are several issues here. Firstly, the probe is not fully inserted into the line. You shouldn't be able to see any thread in the section between the top flange and the winding mechanism. This means the probe is not seeing a representative sample of the flow within the inlet line. Secondly, the probe has been installed at the top of the line, which almost certainly means that should the probe have been correctly inserted into the line, it would almost certainly be measuring at least some air. Hach recommends a horizontal install plus or minus 45 degrees. And thirdly, the probe has been installed adjacent to and upstream of a magnetic flow meter. Most manufacturers require a minimum 5 pipe diameters of straight unobstructed run upstream of a meter and 2 pipe diameters downstream. This is to ensure laminar flow through the measuring tube of the magmeter. If these terms aren't met, the flow meter will not be measuring within the manufacturer's stated accuracy. This picture shows the Hach Solitax probe installed in the outlet of a DAF plant. Again, the probe has been installed incorrectly with the probe at the top of the pipe. At this measuring point, being at the outlet of a DAF, the risk of air being present at the top of the pipe is inevitable. So again, incorrect reading will result. There is one good thing though, the sampling point has been installed adjacent to the Solitax probe, which is an ideal when calibrating the probe. At this location, the outlet of the DAF fed a weir tank, and we recommended that the probe was moved from an in-pipe location to the weir tank, which allowed for the remaining air bubbles in the sample to disperse before the measurement was taken. Thank you very much for listening. That concludes my part of the presentation.
That's great, Martin. Thank you very much. On the surface, it looks like quite an easy process, but it's quite complex, as I think everyone's seen this morning from the presentation. A number of things covered there, and already we're getting some questions through. Just to remind everybody, there should be a panel on your screen where you can type your questions in and send them through to us. And it's my job now to go through those and to relay those to Martin so that he can answer them for you. So the first one we've got here is how would you size a DAF plant for your process?
That conversation really needs to be made with the manufacturer of the DAF plant itself, but it's based obviously on the hydraulic flow, the maximum hydraulic flow that the plant is likely to see. And of course you have to, if you're looking at any increases in plant, or then you need to take that into account. So take into account future expansion, and also what you consider to be the solids loading, because from that the manufacturer can size the DAF tank and the size of sizing the recycle rate, and also the amount of air needed from the compressor.
Okay, that's great. We've got another one here, Martin. Is the Hach TOC online analyzer suitable for oily refinery effluent?
Yes, it is actually. There are a number that we would need to look at the effluent itself, but the main issue with oily samples is that cross-contamination from one sample to another, but we do have cleaning processes on our sampling systems which can use scouring with air and water to flush those residues away to ensure that we're getting a representative sample. But yes, the biotector's digestion process is more than capable of dealing with refinery effluents, and depending on where it is sited, there are ATEX versions as well.
Okay, that's great. The next question we've got is this is a double-barreled one. What is a good benchmark to use to measure the energy performance of a DAF plant? For example, in kilowatts per megalitres treated. That's for potable drinking water. And it goes on to say, does the energy required vary much depending on raw water quality?
Yeah,
so,
I would say you would need to know the inlet flow, the concentration of what it is you're removing, be it solids or an organic load. And obviously you'd need to be measuring the main amount of energy is used by the compressor to saturate the air. So that's your main part. The scraper really is very low energy part of it. But so you'd need to take that energy into account from the compressor and then the load, and look at the if you have in place the analysis of the outlet of the plant, so you can see the efficiency against removal. So that's the way I would go down that. Sorry, can you repeat
so the energy required then, the second part of the question is, does the energy required vary much depending on the raw water quality? So from what you've said already, it's the energy to get the air into the system, and obviously if the raw water is of less quality, let's say, more solids, it will take more energy to do that.
Yes, it's related to the recycle flow rate. Whether it depends on the control system. If the recycle flow rate is tied to the inlet flow, then obviously it will. But as we're proposing, it should be tied to the inlet load rather than the flow. And therefore, the more load, the more energy is needed.
Okay. And I suppose the sizing, coming back to the first question we had, the sizing of the plant is all important as well, because if it's oversized, it would be using more energy than it needs to
exactly.
for the same process. Yeah. Okay. The next one, if there is no particle TOC or particulate TOC, but inorganic suspended solids, then do you regulate coagulation and flocculation only with inlet turbidity?
Yes, you would. If it is truly just inorganic, I'm trying to think of mainly possibly. So I'm thinking aloud here. Sort of, you had some sort of metal flock that metals or sort of clay, something like that, which had a very low density. Then a TOC would not give you a valid result. It wouldn't give you anything. So in that case, you would use a solids measurement.
Right. Okay. Moving on, because the questions are coming in thick and fast now. Do you think it would be worthwhile to use a heat pump to chill the recycled water and use for space heating to reduce the energy costs of the DAF process?
Yes, that's a possibility. I've not seen it done, but there are obviously efficiencies within a heat pump that I frankly have no experience of. But you have heat being generated there because you're compressing air, and so if you can use that elsewhere, and if it's economic and efficient to use it elsewhere, yes, why not? You're saving energy.
Okay. Another customer here who says that we have a DAF that is currently being challenged by algae. The issue we have at the moment is that the turbidity off the DAF decreases at higher flows but increases at lower flows. Could the retention time in the DAF be an issue, or is it more likely to be related to the upstream ozone dose?
So there's an upstream ozone dose as well as that. I mean, that's very difficult to say without looking at the plant. And it sounds like if it's algae, you should be able to remove it with the flock. But it's whether, again, without seeing it, I can't say. So is the flocculant? Maybe you could change flocculant, or if you're dosing a polymer, whether that's has got the right charge. There's several things around flocculation which I haven't gone into because I would have taken hours rather than sort of half an hour in this presentation. You need to adjust those to see what is best to remove the suspended solids that you're dealing with, in this case algae.
So it doesn't seem like it's just about the flow rate coming off the DAF. It's to do with the ozone dose as well, I think, because that may increase or decrease the algae coming
if
in.
you're...
Yeah. Okay. Well, I mean, if need be, Martin, we can take that one offline anyway, obviously.
Yes,
So,
of course. Yeah, we could. Yeah, if it is something that we could look at for them.
Okay. There's a next question here is saying that the person here is interested in this device for a potable water treatment application. Regulation dose is already flow proportional, but could this be used effectively to adjust recirculation flow accordingly?
Yeah. Yes. Again, just the inlet flow isn't sufficient control. You need to know what the load to be removed is. So again, you need to measure turbidity or TOC and adjust your recycle rate and polymer flocculant to that. Really, that would operate the DAF much more efficiently than just flow. As I said previously, a lot of times high flow doesn't necessarily mean high load.
Right. Okay. The next question, why is it better to control TOC instead of turbidity for solids load and efficiency monitoring? Yeah,
it really depends on what we're measuring. If it's as I said before, if it's in an inert material that's inorganic, clays, fine clay suspensions or something like that, TOC would not give you any valid data. However, if it's something like a dairy or sort of abattoirs or something like that, where you have high organic load, then a TOC is. So it really depends on what it is you're trying to remove as to whether it's which way you go, whether you go TOC for organics or suspended solids for inorganics.
And there's also this balance between the solids phase and the liquid phase as well, isn't there?
That's right. Yeah, whether the dissolved organics can be removed as the floc forms. Whether you've chosen the correct polymer and flocculant that can actually remove those, because in drinking water applications, colour, the tannins and the other associated colour chemicals are removed in the flocculation process. So it really depends on what it is you're trying to remove.
Okay, good. The next one here is, how easy is it to retrofit real-time control to an existing DAF plant?
Yeah, it's relatively simple. You'd need some sampling points and have the flow measurements available, and also to be able to control, have a variable speed drive on the recirculation rate, the recirculation water pump as well. After that,
the only intrusive part of the DAF plant is just to measure inlet and outlet, and then, as you say, the control feed goes back to the variable speed drive on the pump that should already be in place. And a variable, and also on the flocculant polymer dosing, they would need to have control inputs as well, rather than manual inputs. Right. Okay. Right. We're getting to the end of the questions now. That we've got another one here. Is there anywhere that the DAF process could not be used?
Crumbs.
Stretching the limitations of the DAF now. Is anywhere that it can't be used?
Yeah, I mean, if your solids are heavy, then you'll be fighting gravity. Some places where you're precipitating out metal salts, which are quite heavy, by increasing the pH to above sort of 10, 11, 12, something like that, to get metal salts to form hydroxides and drop out that way. It would really, sand sort of on a fast-flowing river where the particulates are suspended, but they're relatively quick to drop out, then DAF would not be. It would be.
Yeah. So there'd be other processes.
Yeah.
there be other processes to use in those applications.
Yeah.
Okay, that's great. I think we've come to the end of the questions. There aren't any more, but just to say thank you, Martin, and thanks to everyone for all of the questions. It's been a very good, useful session, I think. Just like to remind everyone on the call that our next webinar in the series, the details are on the screen now. This will be on TOC control for anaerobic digesters. So again, another interesting subject here. We're going to hold that one on Tuesday, November the 14th at 10 a.m. So this will be the last one for this year, and we'll start a new series then next year. So please join us for this one. We'd very much like you to join us and ask you to forward your invitation to any of your colleagues that you'd also think would benefit from attending. So just in case you joined late or one of your colleagues has missed it or anything, just to remind everyone that we record all of these webinars. So we will be able to, or you will be able to watch all of the webinars on our Hach YouTube channel. The link will be sent out to you if you've registered. So that brings us to the end of this webinar. Thank you all very much for attending again, and we look forward to speaking to you again very soon. Thank you very much.